So far, all we've really looked at in terms of the gradient, curl, and divergence is we've always done this in rectangular or Cartesian coordinates. However, we've seen when we were trying to do integrals that a lot of times there are functions in vector fields that work much better when we look in cylindrical and spherical coordinates. So for example, the gravity vector field works much better in spherical coordinates than it does in rectangular. And we usually got around this by just doing more difficult computations using rectangular coordinates. For instance, when we calculated the gradient of the gravity vector field. However, it'd be much easier to be able to work with these things in the correct coordinates, whichever is easier. So what we're going to do in this lecture is go through a lot of calculations to see what is the gradient, the curl, and the divergence when we want to work in spherical or cylindrical coordinates. Now, I've found other videos online that do this, but usually they're very either hand wavy or they require a lot more background than what a normal multivariable calculus student would have. So this should be at the correct level for a student in multivariable calculus to understand. We're not going to do a lot of examples and calculations like we would in a regular class. This is just going to basically establish the formulas for these. So the first thing we're going to need is we're going to need unit vectors. So we need unit vectors in cylindrical and spherical coordinates. Can't really work with any of these vector calculus definitions without unit vectors to start with. So let's start with cylindrical coordinates. So we need unit vectors in the r direction, theta direction, and z direction. Now certainly let's just start with z because that's the easiest one. We already have that one. So we'll write it as ez because we're going to write these a little bit differently, but this is going to just be our k hat vector. So that's just our normal going in the z direction unit vector that we've used all through multivariable calculus. Now let's think about what the other vectors should look like. So since these are in the r and theta direction, we can restrict ourselves to the xy plane. So if we go out to a point here, say this distance is r and this angle is theta, first of all, notice our unit vectors are going to change as we change theta. So the r direction unit vector should be pointing in a little in the direction of r, so it should be here. So we'll write this as er hat. That's in the direction of r. And then for our theta direction, that should be going in the direction of theta, so that should be going in this direction. Right, but the thing to note here is if we change what our theta is, our unit vectors are going in different directions now. So if I change where my r is, for example, so now if r is, say, over here, so this is my theta, and this is my r. Now my unit vector for er is going in this direction. So it's a different vector than what our er was before. And my theta vector is going in a different direction as well. So theta is going like this. So this means these are a little different than what we're used to with the I, J, and K unit vectors because those didn't change at all. Those were always pointing in the same direction. So what do we want for these vectors? Well, we know that ER should be going in the direction of R here. So well, we could write that down. ER hat, this is just cosine theta, sine theta, 0. So that's going in the direction of R. So you go cosine theta in the x direction and sine theta in the y direction. Okay. And then for E theta, well, this must be perpendicular to ER, and it has to be going in the direction of theta. So we can kind of see from this, if we were to redraw this down here, let's put the unit vectors at the origin now. So if my ER say this is ER hat, E theta is going in this direction here. So E theta is going to be given by negative sine theta cosine theta 0. Now, there's another way to do this that isn't just using geometry. We can also say, for instance, that ER, another viewpoint, and this will be more useful when we do spherical coordinates where things aren't quite as obvious, is ER hat should be a unit vector in the direction of a little change of R. Right, so if we have our R up here, right, ER is going just a little bit, change R just a little bit here, and you see this is where my ER is coming from. So if I wanted to figure out the formula that way, I would say, well, take the point x, y, z. In this case, this is going to be r cosine theta, r sine theta, c. And we ask what happens when we change it a little bit. Right, so that's a change in r. Well, then ER hat would be the change in the vector with respect to r and then we want it to be a unit vector, so let's make it a unit vector by dividing out by the length of this vector. And so if we differentiate the first term here, we just get cosine theta. We differentiate the second term, we get sine theta. Now there's no change in z when we change r, so that just gives us 0. And then the magnitude of this is square root of cosine squared theta plus sine squared theta, which is of course 1, so this is just cosine theta sine theta 0, which is what we got from our geometric argument above. And we can do the same process for theta. So E theta hat should be the vector where we change theta a little bit. And then divide that by the length of the vector. And so if we do that, we see on the top I get minus r sine theta, r cosine theta 0. And on the bottom, the length of that is just going to be r. So this gives me exactly what we had above from the geometric argument as well. So those are our unit vectors for cylindrical coordinates. Not too complicated for those. One thing to note is these are all orthogonal. So if I take ER and I dot it with E theta, I get 0. ER dotted with EZ gives me 0. And E theta dotted with EZ gives me 0. And we'll go ahead and check their cross products and everything as well later, but for now, one thing to note is if I take ER cross with E theta, I get EZ. So this is still a right-handed coordinate system. So same thing as before, if you take your right hand, put it along ER, curl it towards E theta, you get EZ, which is quite nice. Okay, so that's how we do cylindrical coordinates. So what about spherical coordinates? Now these are a little harder to draw. And let me just make sure we introduce spherical coordinates, because if someone from physics is watching this, the notation I'll use will be different than what would be used in physics. My notation will match what's normally used in a calculus textbook. So if I take a point and I draw my point up here, the distance here is going to be rho. A lot of physics textbooks use r, but we're going to use rho. The angle coming down from the z-axis is going to be phi. Again, a lot of physics textbooks put that as theta. And when we drop down into the xy plane here, this angle will be theta. A lot of physics textbooks use phi. So for us, so math here, we use rho, phi, and theta. And physics often uses, for these same things, r, theta, and phi. So a little complicated, but I want this video to follow the other videos I've done for the multivariable calculus stuff. So we're going to stick with this notation that I've used before, and this the same notation is used in most calculus textbooks. So in terms of this, we have these representations of our x, y, and z terms in terms of these spherical coordinates. You can figure this out from the geometry if you haven't seen it before. We're not going to go through it here. So we have these. So let's go ahead and figure out our unit vectors again. So E rho, this should be the change. So unit vector with a little change in rho. So what does that mean? Well, this should be the vector given by delta delta rho of rho sine phi cosine theta, delta delta rho of rho sine phi sine theta, delta delta rho of rho cosine phi. And then we're going to say all over the length. Divide by the length. We'll work out the length in a second rather than writing all this out again of numerator. So if we do this, the top part here is just going to be sine phi cosine theta, sine phi sine theta, and then cosine phi, and then over the length of the numerator. So if we go ahead and calculate that length, okay, so everything should be pretty familiar right now compared to what we did above. So if I calculate that length, I'm going to get, let's say, length of the numerator squared, just to make it a little bit easier. So we have to deal with the square root. So I'm going to this squared plus this squared plus this squared will be the square of my length. So this is sine squared phi cosine squared theta plus sine squared phi sine squared theta plus cosine phi squared. So that first term, I factor out the sine squared phi, and I get cosine squared theta plus sine squared theta plus cosine squared phi. Notice in the parentheses that's equal to 1, so this is sine squared phi plus cosine squared phi, and that's of course just 1. So the thing is already a unit vector, so E rho is going to just be what we found on the top. So this is just sine phi cosine theta sine phi sine theta cosine phi. So that's our first unit vector for spherical coordinates. And now we can do the same procedure for the next two unit vectors. So let's look at E of phi hat. So this is going to be take the derivative of the top part, and I'm going to leave some of these calculations out, and we'll just figure, if you want to check all the details, which you probably should, just go ahead and take these derivatives, and you'll see where all of this is coming from. So we take the derivative of everything of the x, y, and z in the top, and we get that. And then if we look at the length of that vector on the top, it's the same thing pretty much as before, just with a rho out front of it. So we get that rho to divide out, and I get cosine phi cosine theta cosine phi sine theta minus sine phi. And that's my unit vector in the direction of phi. And then finally, for the last one, E theta, well, we already calculated this before when we were doing cylindrical coordinates, but let's just do the calculation again to see what we would get out of this. Well, if I take the derivatives, I get sine phi sine theta, rho sine phi cosine theta, and then 0 for the last term. And then I have to divide by the length of this. Well, the length of the top is sine phi, and we can just use parentheses here because of our limit on where phi is makes that always positive. And so if I divide out by that, I get exactly what we had before, which is minus sine theta cosine theta is 0. So exactly what we had before. And again, we can check that they're all orthogonal. So I'll leave that for you to do as calculations, but if I dot these together, I get 0 for all of these. And finally, if I take E rho and I cross it with E phi, I get E theta. So again, we get a nice right-handed coordinate system here. So what's our next step then? So what we want to do next I want to calculate what this del operator is in cylindrical and spherical coordinates. So for our first step in this calculation, let's calculate a couple of chain rules. So we want to calculate del f for a function f. So a couple of chain rules that are going to be useful for us here is the partial derivative of f with respect to r. So this is partial of f with respect to x, partial x with respect to r, plus partial f with respect to y, partial y with respect to r, and then partial f with respect to z, partial z with respect to r. And so now if we just calculate these out, this first term here, this is just partial, we'll just write it with f sub x to ease our notation. If we take the partial of x, remember x is r cosine theta, y is r sine theta. So I take the partial of that with respect to x, I'm just going to get a cosine theta. And similarly here, I'm going to get a sine theta. And then z doesn't change with respect to r, so I'll just get a plus 0 there. And then do the same thing with respect to theta. And again, we see we get f sub x. And then if I take the derivative of this with respect to theta, I'm going to get a minus r sine theta. So f of x times minus r sine theta. It's not a composition. And then I'm going to get r cosine theta. And of course, z doesn't change with respect to theta. So that's going to just stay the same. So these are going to be important for us in a moment. So let's just keep these in mind in a few minutes. So now let's suppose we have, so the gradient of f, let's write this in terms of our new unit vectors for cylindrical coordinates, and I don't know what the coefficients are going to be yet. That's what I want to find. So let's just write these as a, b, and c, and our goal is to find what these are. So let's find a, b, and c. So what we also know is we know from before that if I take the gradient in rectangular coordinates, it's just given by this. In this k here, this is ez hat, just to remember that. Now let's take this equation up here and let's dot that with er. So if I take the gradient of f and I dot this with er hat, well, I'm going to get a er hat dot er hat plus b e theta hat dot er hat plus c ez hat dot er hat. And we know those are all orthogonal except for the first, so this just gives me a. So that gives me one calculation, but I can also take and dot the rectangular coordinates with that. So if I take gradient of f and dot it with er hat, it's also equal to fx I dot er hat plus f sub y j dot er hat plus f sub z k dot er hat. And now we just use our definitions for er hat and just do these calculations. So I have I dotted with, and let's sub in what er hat is. So remember that's cosine theta I plus sine theta j plus fyj dot, and then er, again, cosine theta I plus sine theta j. And then the last one, of course, there's no k component, so that will just go away. So this becomes fx, and then I have a cosine theta. I dot I is 1, I dot j is 0, so that goes away, plus fy, and then I'm going to get a sine theta. So this is, since gradient of f dot er, since these are, of course, equal, and on the one hand we have it's equal to a, on the other hand we have it equal to this, so my coefficient a is given by this value from our calculation. But notice the two calculations we did above, that's exactly the partial of f with respect to r. So this is exactly del f del r. So our first calculation is that we get the coefficient of er hat is del f del r. And now we can play the same game with e theta. So I'm going to take b, which is the gradient of f dot e theta hat, just like above how we got the a. And now we just do the same procedure. And so again, we just go through this calculation, and I have I, and then I dot it with, and we just fill in what our e theta was. And we get this, and so then we simplify this. We have minus sine theta f sub x plus cosine theta f sub y. So that's equal to my b. And then again, if we look above, that was exactly, it's almost exactly this thing here. So notice the only difference is we had an r in this. So we could have rewritten this as r times f sub, let's change the order to where we're at it, minus sine theta f sub x plus cosine theta f sub y. So we have that extra r there. So this isn't equal to just that value. This is equal to 1 over r del f del theta. Right? So if we could rewrite this as 1 over r times minus r sine theta f sub x plus r cosine theta f sub y. Notice since I'm multiplying by 1 over r and r, I'm just multiplying by 1, so I haven't changed anything there. And we can also calculate, we're not going to because it's straightforward, that c is just del f del z. Nothing's really changed there. We're still using the same z component. So if we do that, what have we just shown? We've shown that the coefficient of er hat is the partial with respect to r, and then we had 1 over r del f del theta for e theta hat, and then just del f del z for ez hat, which is the same as k hat. So then we could write just the del operator. If we want to not have a function there and just write it as an operator, we can write this as er hat, no f now, del r plus e theta hat 1 over r del theta plus ez hat del z. So that's our del operator in cylindrical coordinates. So that wasn't too bad to do. And now if we have a function in cylindrical coordinates, we can calculate the gradient of it without having to convert it to rectangular coordinates first. So now let's go ahead and do the same thing for spherical coordinates. We're going to follow pretty much the same procedure. So of course, if this seems easy, you can skip ahead to just get to the answer, but we're going to include all the details. So in case it isn't clear, we have this. So we're going to start with doing the same calculations for the chain rule again, just like we did above. Okay, and so if we do this one out, what we get is f sub x sine phi cosine theta plus f sub y sine phi sine theta plus f sub z cosine phi. So that's the first equation that's going to be useful for us. And now we want to do the same thing for the others. Maybe I'll just write these down because these are just straightforward derivatives. And so the last one, we take the derivative with respect to phi, we're going to get a negative. So we get f sub 0 sine phi. And then same thing, same process, you're just using chain rule. So just go through the same thing. And so I'm going to get a rho sine phi sine theta plus f sub y rho sine phi cosine theta. Okay, so now we've calculated these derivatives that are going to be useful for us, and now we do the same thing we did before. We write this as a e rho hat plus b e phi hat plus c e theta hat. And so same process, we're going to say a is equal to the gradient of f dotted with the e rho hat. That picks off our a component. And now we're going to just go ahead and do this as f sub xi plus f sub y j plus f sub z k. And we're going to dot that with e sub rho, which is sine phi cosine theta I plus sine phi sine theta j plus cosine phi k. And if we do this dot product, we get f sub x sine phi cosine theta plus f sub y sine phi sine theta plus f sub z cosine phi. And if we look above, this is just exactly df d rho. So that gives us our first one. Let's go ahead and write it down and circle it so we can easily find it when we come back. And now we're going to do the same thing for the other ones, other coefficients. So this is e phi hat. So just like above, this is f sub xi plus f sub yj plus f sub zk. And then we dot this with e rho, which is rho cosine phi cosine theta I plus rho cosine phi sine theta j, and then minus rho sine phi k. And so this is equal to f sub x rho cosine phi cosine theta plus f sub y rho cosine phi sine theta minus f sub z rho sine phi. And this looks a lot like what we had before, except for there's a rho in there, so let's factor that out. So we have this. Oh, we made a mistake here. Sorry, there should be no rows in this because of the unit vector doesn't have any rows in it. So this should be a cosine. Let's get rid of these rows. Of course, we can have row in our unit vector, so there should be no row there. There we go. So it's this. And this looks an awful lot like what we have above here with the df d phi. Notice those are almost the same except for there's an extra row above. So this is 1 over rho df d phi. Sorry about that mix up with the rows there. And finally, the last one's a little bit more complicated. Not too bad, but let's go ahead and see how it works. So we're going to do the same thing again There's at least less terms this time, so that's always great. So we have this. So our dot product here is just minus f sub x sine theta plus f sub y cosine theta. And if we look back above, it looks an awful lot like this one, except for there's a row, an extra row here and an extra sine phi here. So this is equal to 1 over rho sine phi times del f del theta. So then if we've calculated all this, what we found is that this is del f del rho e rho hat plus 1 over rho del f del phi e phi hat plus 1 over rho sine phi del f del theta e theta hat. And if we want to write this just in terms of an operator, we can write this as e rho hat del del rho plus e phi hat 1 over rho del del phi plus e theta hat 1 over rho sine phi del del theta. So now we have the gradient for cylindrical and spherical coordinates. Our next step is going to be to calculate the divergence. Normally we sometimes learn about curl first, but curl is going to be messier to compute. So we're going to go ahead and start with divergence next. So what about divergence in cylindrical coordinates? Start with cylindrical, and then we'll move to spherical. And these require some calculation. So what should this be given by? Well, it should be, for a vector field, we should take the del operator we found above for the cylindrical coordinates, which was right here, and we should apply that to our vector field. So this should be that thing we found, er hat del del r plus e theta hat 1 over r del del theta plus ez hat del del z, and we want to apply this to our vector field, which we'll write as f er hat plus g e theta hat plus h ez hat. All right, so we're writing our vector field here in cylindrical coordinates as well. So now what makes this a little bit more complicated is, remember, our er and our e theta, these are not constant. Remember, we saw both from the formulas and from the pictures that as I change theta, both of those vectors change. So when I apply these derivatives, I'm going to have to use product rule, because when I take the derivative of this, for example, f changes and er hat changes. So let's recall that we have er hat is cosine theta sine theta 0. So this changes with theta only. So if I take the derivative of er hat with respect to r, that's going to give me the 0 vector. And if I take the derivative with respect to z, that's going to give me the 0 vector. However, if I take the derivative with respect to theta of er hat, this becomes minus sine theta cosine theta 0, which is exactly e theta hat. And similarly, with e theta hat, I have that this is minus sine theta cosine theta 0. So this doesn't change with r or z either, but if I take the derivative of it with respect to theta, I get minus cosine theta minus sine theta 0, which is exactly negative er hat. So those are going to be important when we do our calculations. So now that we have that, let's go ahead and calculate our divergence. So remember, this is er hat, and then what I do is I take this operator and I apply it to my vector field. So I have erase the parenthesis and put it back. Del r of my vector field, which is f er hat plus g e theta hat plus h e z hat. And then I have plus e, this should be dotted with this now because we're taking the dot of the divergence with this. So plus e theta hat dotted with 1 over r, and then I have del theta of f er hat plus g e theta hat plus h e z hat. Finally, plus ez hat dotted with just the derivative with respect to z of f er hat plus g e theta hat, wrote that wrong, g e theta hat plus h e z hat. So most of these aren't going to be so bad to compute, so let's just leave our er hat there for now and dot it. And now remember that all of the unit vectors were constant with respect to r. So this will just become fr er hat plus gr e theta hat plus hr ez hat. Now the next one's a little trickier. So I'm going to have the e theta hat and leave that alone. And dotted with, let's leave the 1 over r there. But now when I take the derivative of the first term, I'm going to have f theta er hat plus f, and then I need the derivative with respect to theta of er hat, and then plus, same thing for the other ones, g theta e theta hat plus g derivative with respect to theta of e theta hat. And now we know that ez is constant with respect to theta, so this just becomes h theta ez hat. So notice these we're using product rule for both of these, because that derivative of the e theta hat is not constant. And then for the last one, I have ez hat dotted with, and then I'm going to have f sub z er hat plus g sub z e theta hat plus h sub z ez hat. So we can start doing some simplifying here. So for the first one, we know the dot's going to kill everything out except for the f sub r, so I'm just going to get an f sub r from that. For the second term, I have 1 over r. And now remember, we calculated these derivatives of this. So the derivative, let's go ahead and put these in. So remember, this derivative here, this is e theta hat. And this derivative here is minus er hat. And since we're dotting this with e theta, we're not going to care about that second one. That's going to just go away. So I'm going to have 1 over r. I have f theta. Well, let's leave our e theta. We'll do this one in a little bit more steps. So e theta hat dotted with 1 over r, and I have f theta er hat plus f e theta hat plus g theta e theta hat, and then minus g er hat plus h of theta ez hat. And then for the last one, we can just dot that out, and that just gives me h of z. And so finally, the last calculation, dotting with the e theta, I'm going to have 1 over r, and then I have an f for the e theta dot e theta plus g of theta, and then there's no more e thetas there, and plus h of z. So the shorthand way to write this that you'll see in books is they're going to combine these f terms. We're going to write this as 1 over r del r rf plus 1 over r del theta of g plus del z of h. And so you can just check that this term here, you use product rule on it, so that gives you a, when you take it with respect to r, I just get f plus the r times the derivative of f, and that's going to give you these two terms here. So that's the way it's going to be written in books, so it's good to go ahead and see that what we have is the same as that. Now, the spherical coordinates are a bit more of a pain to do, as you might imagine. So we're going to have our, so let's say we're going to spherical coordinates next. We're still doing the divergence for now. What we're doing now will help some when we're doing the curl as well. So let's say our f now is given by f e rho plus g e phi plus h e theta. And so what we're going to have is when I take the divergence, remember this is going to be e rho del del rho plus e phi 1 over rho del del phi plus e theta 1 over rho sine phi, and then I'm going to have del del theta, and we're applying that to f e rho plus g e phi plus h e theta. So just like before, our unit vectors are going to change here. And there's no change with respect to rho for any of them, so we can ignore that one. But we do need to calculate with respect to the other ones. So if I take e rho with respect to phi, this gives me cosine phi, cosine theta, cosine phi, sine theta, minus sine phi. And if you look back, this is exactly e phi hat. If I take with respect to theta of e rho hat, this gives me minus sine phi, sine theta, sine phi, cosine theta, 0. And you can check this is exactly sine phi times e theta hat. And then we can go through and do the other calculations as well. So d phi of e phi hat. So I'm just going to give the answers here rather than doing all the calculations. This is minus e rho hat. Delta delta theta is of e phi hat is cosine phi e theta hat. So those ones aren't too hard to calculate. And then if I do d phi of e theta hat, I just get 0. And then this one's a little complicated. So this one doesn't look exactly like anything we have if I take the derivative. But of course, it has to be a linear combination of our basis vectors because they're basis vectors. So this is minus sine phi e rho hat plus, or minus still, minus cosine phi e phi hat. And you can go ahead and verify that by just checking the right-hand side is equal to that. Now that we have all these, we can calculate the divergence. So again, I have the divergence of f is e rho hat dotted with, and I'm going to have d rho of f e rho plus g e phi plus h e theta plus e phi dotted with 1 over rho. I have d phi of f e rho plus g e phi plus h e theta. Finally, e theta hat dotted with 1 over rho sine phi, and then delta theta of f e rho plus g e phi. So g e phi plus h e theta. And we're going to calculate each of these separately because they're a bit of a mess. So let's take the first term. Remember, all of our unit vectors are constant with respect to rho, so this is by far the easiest one to calculate because this is just e rho dotted with f rho e rho plus g rho e phi plus h rho e theta, and so this is just f rho. So that one's super easy. The next two are going to be a little bit more complicated. So let's start with e phi dotted with 1 over rho, and then I have delta delta phi of these terms. And now we are going to have to use a product rule here because the unit vectors change with phi. So this is E phi dotted with 1 over rho. And now I have to use the product rule here. So this is F phi E rho hat plus F, and then the derivative of E phi, remember, so this is the derivative of E rho with respect to phi is E phi hat. So go back up here. Derivative of E rho with respect to phi here is just E phi. So we're using this one. So that's our product rule for the first term. And then we get a G of phi E phi hat plus G, and then the derivative of phi with respect to E phi with respect to E phi was minus E rho. And then finally, the derivative of E theta with respect to phi was 0, so then I just get an H phi E theta hat. So if I calculate all of this, I have E phi dotted with 1 over rho, and then I get, gathering all the vectors together, I'm going to get a F phi minus G E rho hat plus F plus G phi E phi hat plus H E theta. And since I'm dotting with E phi, this just gives me an F plus G phi. And finally, the last one for this. So E theta dotted with 1 over rho sine phi, and then I have delta delta theta of our vector field here. So this is E theta dotted 1 over rho sine phi. Oh, I'm thinking, I missed anything up here? Yeah, I should have a 1 over rho here. Sorry, I lost that 1 over rho. So 1 over rho sine phi, and then delta delta theta of these things. So let's just go ahead and start taking these derivatives. So I'm going to get an F theta E rho hat, and then I get plus F, and then the derivative of E rho with respect to theta, let's go up and see that. Derivative of E rho with respect to theta was sine phi E theta. So this becomes sine phi E theta hat. And I have to do the same thing with G. So I'm going to get G theta E theta plus G, and then the derivative of E phi here, go back up, phi with respect to theta was cosine phi E theta. Wait, did I write that one right? So derivative, we want the derivative with respect to theta of E phi. So derivative with respect to theta of E phi is cosine phi E theta. Yep, so I got that right. And then the last one, I'm going to get H theta E theta hat. And then this is where we have the messy one. So remember, this was minus sine phi E rho hat minus cosine phi E theta hat, or E phi hat. Check that, make sure that was right. Yeah, E phi. So I'm dotting with this with E theta. So really all I care about is what the theta terms are, and that ends up being a rho sine phi. And then what I have left is F sine phi, and then plus G cosine phi plus H theta. And if we want to combine this, this is 1 over rho F plus 1 over rho tangent phi G plus 1 over rho sine phi H theta. And so putting all of this together, this was a giant messy calculation. Don't forget we still have to do the curl, which is going to involve cross products. So F rho plus 1 over rho F plus 1 over rho g phi plus 1 over rho f plus 1 over rho tangent phi g plus 1 over rho sine phi h theta. And the short way to write this that most books will use, and you can verify, this is 1 over rho squared delta delta rho of rho squared f plus 1 over rho sine phi delta delta phi of sine phi g plus 1 over rho sine phi delta delta theta of h. I'm not exactly sure why that's so much better of a formula, but that is the way you'll see it in most every book. So you can verify that those two formulas that are given there are actually equal to each other. Okay, so finally we're going to move on to the curl. First in cylindrical coordinates. So we don't want to use the matrix definition that we use for rectangular coordinates here because that's not going to actually give us the correct answer. So what we want to do is we want to remember that the curl of our vector field is the del operator crossed with the vector field. So in this case, this is ER hat. So let's write down our del operator first. And we're going to cross this with FER plus G E theta plus H EZ. So let's think about what's going on here. So this is ER, and then it's going to cross with delta delta R of FER hat plus GE theta plus H EZ. Got too used to the cylindrical coordinate or the spherical coordinates there. And then I move to the next one, so I have a plus E theta cross 1 over R delta delta theta of FER hat plus G E theta hat plus H EZ hat plus finally EZ hat cross delta delta Z of FER hat plus G E theta hat plus H EZ hat. And now we can simplify these a bit. So I have ER hat, and now this first one, we know this is just F sub R ER hat plus G sub R E theta hat plus H sub R EZ hat. The second one, remember, is a little more complicated because when we take the derivatives of those, the unit vectors, they're not necessarily constant. So this becomes my F of theta ER hat plus F E theta hat plus G theta E theta hat minus G ER hat plus H theta EZ hat. And then finally the last one, EZ hat cross, and then I'm going to have F sub Z ER hat plus G sub Z E theta hat plus H sub Z EZ hat. Now the only thing left to do is do all these cross products here. And since these are basis vectors, that's not so hard. So we use, now you can compute these out if you want from the formulas, or you can just go ahead and look at the pictures. We have ER hat cross E theta hat. This is exactly EZ hat. So of course, if we change the order, then we just introduce a negative sign. And similarly for the other ones. So what do I mean by just, you can calculate these out by the formulas? Well, we know what these vectors are in terms of their ijk components, and so then we can use the matrix definition in that case. So maybe let's do one of them after I write all these down, just to make sure it's clear what I'm saying. So E theta hat cross EZ hat is ER hat, and EZ hat cross E theta hat is minus ER hat. So let's just do one of them. So if we do E theta hat cross EZ hat, this is really the vector. Remember, theta, E theta is minus sine theta cosine theta 0, and then we're crossing that with 0, 0, 1 in our cylindrical, or in our rectangular coordinates. So then we can use this matrix definition for the cross product. So minus sine theta, cosine theta, 0, and 0, 0, 1. So if I write that out, for the first term, I'm going to get cosine theta I minus, and then I cover up the other ones, I get minus sine theta j, and then for the last one I get 0. So this is exactly ER hat. So you can use the geometry or you can do those calculations. But now we just go back up here and we distribute these through. So if I do the curl now, this is FR ER hat cross ER hat plus GR ER hat cross E theta hat plus HR ER hat cross EZ hat. And then we continue with the rest of them, 1 over R F theta E theta cross ER hat plus 1 over R F E theta cross E theta plus 1 over R G theta E theta cross E theta minus 1 over R G E theta cross ER plus 1 over R H theta E theta cross EZ. So that's just distributing, going up here and just distributing these vectors through all of them to get this. And now we just use our relations that we just found above. Oh, we're not quite done. Sorry, I missed a few here. Plus F sub Z EZ hat cross. Yeah, forgot the last batch of them. Now remember, any vector crossed with itself is 0, so that's going to eliminate a bunch of these. And now we just use our relations, so we have GR, and we had ER cross E theta was EZ, and then minus HR E theta, because ER cross EZ was negative E theta, and then we just go through and fill in the rest of these cross products from what we found. We get F theta EZ hat plus 1 over R G EZ hat plus 1 over R H theta ER hat plus F of Z E theta hat minus G of Z ER hat. And if we write all of this down, gather all these, I get 1 over R H theta minus G of Z ER hat plus F of Z minus H of R E theta hat plus G sub R minus 1 over R F theta plus 1 over R G EZ hat. So that's our curl. And now if you did want to write it in terms of a matrix, so I'll do it for this one. I'm not going to do the matrix for the spherical because it's really not that important. You might, if you're going to ever use these formulas, you're not going to memorize them anyway, so you're just going to look them up. So the whole point of this is just to show you where these are coming from, so they're not like mysterious. But we wouldn't actually derive these out every time. So instead of just putting the unit vectors across the top, I need a R there with my E theta, EZ, and then I do del del R, del theta, and then del Z. And the bottom I put an F, but then I need to put an R with my G, and then my H. And then you can use the same process we've used before to calculate that determinant. So notice there's 2 spots where we have to introduce an R here to make this work with the matrix. That's why we can't just use the matrix definition to start with. We have to insert these things to make it work so that it actually matches this formula that we calculated. Okay, so the very last one we need to do is now spherical coordinates. So let's switch to that. And we're going to need to do these same cross products. So let's note that if I have E rho going like this, E phi is going to be going down like this, and then E theta is kind of going something like this. So again, you can use the formulas if you'd like to work all these out. I'm going to just give them to you. You can kind of figure these out from the picture here. But again, if you're not sure from the picture, you can just write down the formulas just like we did above and see what all of these things are. But I don't want to spend, this video is already turning out to be quite long, so I don't want to spend time just doing a bunch of cross products on the video. If you've made it this far, you can certainly calculate these simple cross products. If you've made it this far through all these calculations, I'm quite impressed that you've stuck through it. This is a lot of kind of tedious calculations, but like I said at the beginning, I didn't find anywhere else where I could find these calculations done this way that I thought didn't require any extra knowledge. These are a little long to do, but at least we don't need extra knowledge for this. Okay, so now let's do our curl. Going to be messy, but we know how to do it at least. So even though it's a messy calculation, we know what we're doing. So I'm writing down my del operator first. I'm applying this. I'm going to cross this with f e rho plus g e phi plus h e theta. And if I do all of this, this gives me e rho cross del rho of f e phi, or f e rho plus g e phi plus h e theta, and then plus e phi cross 1 over rho, and then del phi of same thing. I write the last one. Now remember, these derivatives, turned out there are a bunch of them that were not zero because these unit vectors are changing like crazy. So we have e rho, and then I'm going to cross this. Now I'm going to do this calculation. So I have f rho e rho hat. And the rho ones were fine, so this just came out normal because nothing had a rho in it when we did the unit vector. So that one's easy. But now the next one's going to be messy. So the next two are going to be messy, actually. So e phi, and then I cross, I have my 1 over rho, and then I get an f phi e rho hat plus f, and now when I differentiate e rho, remember I had e phi plus g phi e phi hat, and minus g e rho hat plus h phi e theta hat plus h, and then we had a 0 for that term, for the derivative of theta with e theta with respect to phi. And then find the last term, e theta hat, cross 1 over rho sine phi, and I have f theta e rho plus g theta e phi hat plus g cosine phi e theta hat plus h theta e theta hat plus h times minus sine phi. So these are just using all the derivatives we already calculated of these unit vectors. Okay, and now we just go ahead and do the cross products. We have all these cross products from above, so we just do those. And so if we do that out, I get a g rho e theta hat minus h rho e phi hat minus 1 over rho f phi e theta hat plus 1 over rho g e theta hat plus h phi plus, say, let's keep the rows out front, 1 over rho h phi e rho hat plus 1 over rho sine phi f theta e phi hat minus e phi hat minus g theta e rho hat minus h sine phi e phi plus h cosine phi e rho. So go ahead and probably at this point be good to pause the video and do those cross products, at least some of them, to make sure you understand where everything is coming from here. And then if we put this all together, this is a 1 over rho. Let's just factor that 1 over rho out front of everything. 1 over rho, and then I get a h phi plus 1 over sine phi, and then h cosine phi minus g theta. And this is my e rho term, plus g rho minus 1 over rho f phi plus 1 over rho g phi theta hat plus 1 over rho sine phi f theta minus h sine phi minus h rho e phi, or e. Yeah, I wrote these in the wrong order. Normally I do e phi and then e theta, so let me switch that order up for this. So we rewrite this 1 over rho h phi plus 1 over sine phi h cosine phi minus g of theta. So we do usually write the e rho first, but then it's normally e phi next. So let's do it that way, especially since it can be confusing, the rhos and the phis and the thetas. If you're coming from physics, it's a little confusing anyways to start with. So let's keep them in the correct order as best we can. So that's our formula we've derived. And now if you look in a textbook, it's going to look a little bit different because they're not going to do the derivation for you. They're just going to tell you what the answer is. So you can match these up if you like. Just take 5 minutes and go ahead and calculate these derivatives and simplify. I don't know that it's particularly better in this form, in my opinion, but it's fine. I want to make sure that we see you have the correct formula so you see that it matches the textbooks as well. Just be careful if you're looking at a physics textbook, because the rho might be written as an R and the phi and theta might be switched, so it can be a little confusing. And that's it. So if you've made it all the way to the end of this, I am impressed, but there are the derivations for the unit vectors, and then the gradient, the divergence, and the curl, and cylindrical and spherical coordinates. Now you can do these calculations for change of coordinates, for arbitrary change of coordinates, but it's a little bit more complicated and it requires some more background. So for the most part, for Calculus 3, you're usually only using rectangular, cylindrical, and spherical coordinates. If you need more than that, then most likely you're a little further on in your studies and you can understand the more general version of change of coordinates for these things.